Optimization sounds like a fancy technical term, but you can really think about it as finding the largest point in an area, right? The highest point in an area, or the lowest point in an area. And this is an important concept both in mathematics and in related fields. It is often introduced in calculus courses, but it has applications in other fields in mathematics. Some things that come to mind are the maximum likelihood estimator. It comes up in mathematical modeling. And outside of mathematics, it's an important concept in topics such as economics, right? The idea of allocating scarce resources. Hello, welcome back to the Quant Plus YouTube channel. Today, we'll be discussing the idea of optimization. As we mentioned in the intro, this idea is often brought up during calculus courses, and that's the lens that we're going to take to look at it today. So, to begin, let's review the single variable case. In the single variable case, the idea is this. You find the first derivative, and you set it equal to 0. And if c is some value such that the first derivative at x equals c equals 0, then c is a critical point, right? Essentially, c is a point of interest to us. And then from there, we have our second derivative test. So what does our second derivative test say? If we are located at a critical point, i.e. f prime of c is equal to 0, and our second derivative is greater than 0, then we're at a relative minimum, right? And you can see that in the drawing here. If, on the other hand, we're at a critical point again, right? F prime of c equals 0, but f double prime of c is less than 0, then we're at a relative maximum, and we can see that in this picture here. The reason I drew those pictures is because I think many people have ridden a roller coaster at least once, and how it can be helpful to think about it as the relative minimum happens at the bottom of the hill. And what do we experience at the bottom of the hill? Momentarily we stop, right? So if we take the physics perspective of it, the derivative of our position function is our velocity function. And by setting the velocity function equal to 0, our velocity is temporarily 0, right? i.e. we're for a fraction of a second, we're paused at the very bottom, right? We're stopped at the very bottom. And then our second derivative of our position function is our acceleration. If our acceleration is positive, which in the norms of physics and everyday life, right, we're going to treat upward or increasing our altitude as positive, then okay, that's describing what's happening at the bottom of the hill, right, or like in a valley, where we're momentarily stopped, but we're moving towards upwards, right? Our angle is upwards, and we're going to push ourselves upward. And the relative maximum is pretty much what happens at the top of a hill, the exact opposite case. We're momentarily stopped at the top of the hill, and we're about to get pulled downward by gravity, and we can think about that as having a negative acceleration. So in terms of a mathematical context, let's take a relatively simple example. Let's say we have the function y equals x squared minus 1. Our first derivative is going to be 2x, and our second derivative is going to be 2. What this shows is because the second derivative is 2 and 2 is positive, if we find a critical point, then it has to be a relative minimum. To continue the process, our first derivative, which was 2x, is equal to 0, therefore x equals 0. And our second derivative at x equals 0 is 2, which is positive. So from these two pieces of information, we can conclude that x equals 0 is the location of a relative minimum. And if we take the graphical perspective on things, and we sketch y equals x squared minus 1, right, we end up with something like this, where this point right here is at x equals 0, and we can see that that's the lowest point, right? That's also the vertex of our parabola. If we jump to the multivariable case, we have a similar idea, but now instead of a function of one variable, let's just say x, we have a function of two or more variables. And what I wrote out here are the conditions for finding a relative extrema in a case where we have a function of two variables. So in the multivariable case, our first step is to find our gradient, right? Which in the two variable case, if we have f as a function of x and y, then our gradient of f is the first partial with respect to x and the first partial with respect to y as a vector, right? So this is the first component of our vector and the second component of our vector and so on. And we then set this gradient equal to 0, and we have to solve a system of equations to find our critical point. We then have an idea, the Hessian matrix, right, which is analogous to our second derivative in the single variable case. And the 2x2 Hessian matrix is written out here. It's the second order partial derivative of f with respect to x twice. The mixed partials right here and right here, and by the equality of mixed partials, if we differentiate with respect to x first and then y, or otherwise y then x, these are equivalent. And then finally the second order partial with respect to y twice. If we find the determinant of the Hessian matrix, we can find it with this formula written here. Right, this is the standard formula for a determinant. Pretty much you multiply along the diagonal in the 2x2 case and then subtract away what's not on the diagonal. In this case, what's our mixed partials. We have a few additional conditions, right? So, okay, our first condition is to say we are at a critical point, meaning the gradient function at some point C is equal to 0. And if the determinant of h is greater than 0, at that point in our second order partial derivative, the one top left corner is positive, then we have a relative minimum. If we're at a critical point, our determinant is greater than 0, and our second order partial with respect to x twice is less than 0, we have a relative maximum. And if we're at a critical point, but our determinant of our Hessian is negative, then we're at a saddle point. So let's discuss these cases. What we want to think about is that how we found the determinant of h. If the determinant of h is positive, then that indicates that this first term here is positive, and because that's positive, that shows that they have the same sign, right? D squared f dx squared has the same sign as d squared f dy squared. And then from there, okay, that if either of those is positive, then that's a relative minimum for reasoning pretty much identical to the single variable case. And you can think about it as, okay, instead of being in a 2D plane, you're in a multivariable, let's just say you're in a 3D world like our real world, and you're at the top of the mountain. Sorry, at the bottom of the valley. Similarly, for the relative maximum, right, we're at a critical point. Because our determinant is positive, our first term that we underline in blue is positive, and the same argument holds from before. But now, if d squared f dx squared is less than 0, then it's very analogous to the case of the relative maximum in the single variable case, right? Now you're at the top of the mountain. As for the saddle point, a saddle point occurs where pretty much along one axis, you have a point appears to be a relative maximum, and along a different axis, your point appears to be a relative minimum. So let's discuss an example. If we have f of xy defined as it is here, x squared minus 10x plus y squared minus 12y plus 71, well, let's start off by finding the partial derivative with respect to x. And we get 2x minus 10. And then our partial derivative with respect to y is going to be 2y minus 12. Being a little bit lazy about notation, if we set this equal to 0 and this equal to 0, the reason I'm being a little bit lazy about notation is because there's no term that involves both x and y, and this is essentially a separable case. From here we get that x is equal to 5 and y is equal to 6. So that means that the point 5, 6 is a critical point. And then from here, our second order partial, right, d squared f dx squared is going to be 2 d squared f dx dy, right, meaning take the partial derivative with respect to x of our partial derivative with respect to y, we get 0. By the equality of mixed partials, it should be the same as taking the partial derivative with respect to y of the partial derivative with respect to x, but we can double check that. The second derivative of f dy dx, the partial derivative with respect to y of this here is also going to be 0, right, which holds by the equality of mixed partials, and that makes sense. And then finally, d squared f dy squared is 2. We can find our Hessian matrix is this one right here. And the determinant of our Hessian matrix H is going to be 2 times 2 minus 0 times 0, right? So that's going to be 4. And more importantly, 4 is positive, okay? So that means that we have a relative extrema, right? It's going to be either a relative maximum or a relative minimum. And then from here, our d squared f dx squared term, which is in the top left corner, is 2. And so because this value is 2, and 2 is positive, that means that our point that we found, right, 5, 6, is a relative minimum. And another example I wanted to bring to your attention is that of a saddle point. Now, there are many, many such functions, but let's just look at one like this. Now, notice that if we consider y being 0, right, then we have z equals x squared. And so in the xz plane, we have a parabola that opens upwards, and therefore we should have a relative minimum. On the other hand, if we consider x is equal to 0, then we're left with z equals negative y squared, and in the yz plane, we have a parabola that opens downward, and we should have a relative maximum. So let's try and sketch that out here. Okay, so we start off with y being 0, so we end up with something like this, right? In the xz plane. And if x is equal to 0 and we're in the yz plane, then we have a parabola that opens downwards because we have z equals negative y squared. And we can see that at the origin, right, at 0, 0, 0, if we are in the xz plane, it looks like a relative minimum. If we're in the yz plane, we're looking at a relative maximum. And that's an example of a saddle point. Applying what we're considering in terms of our rules for finding a relative extrema, let's find it. So our partial derivative with respect to of z with respect to x is 2x. Partial with respect to y is minus 2y. That means that our gradient of our z is this one. And to be a little bit more formal about our notation, if we set this equal to the zero vector, then we end up with 2x is equal to 0 and x is equal to 0. Negative 2y equals 0, so y equals 0. And then plugging in, we have z is 0 squared minus 0 squared, and that's 0 as well, right? So the point that we're considering, the origin. Taking the next step, we look towards our second derivative, right? So d squared z dx squared is 2. D squared z dy dx is 0. D squared z dx dy is also equal to 0. And finally, d squared z dy squared is negative 2. That means that our Hessian matrix is this one, and that our determinant of our Hessian matrix is 2 times negative 2 minus 0 times 0. This is negative 4, and the important point is that this is negative. So according to our rules, this should be a saddle point. And graphically, we see that that's exactly the point, right? That's exactly what we see here. There are two more points I wanted to bring up. The first one being that both in the single variable case and in the multivariable case, these tests are not always conclusive. So jumping back to the single variable case, right here. What I failed to mention earlier is that if we have a critical point, right, our first derivative is equal to 0, but our second derivative equals 0, then this test is inconclusive. Similarly, in the multivariable case, we wrote out these three cases, but technically there's a fourth case. And that fourth case is if our determinant of our Hessian matrix is equal to 0, then we don't have a conclusive result from this test. And the last point I wanted to bring up is there are other techniques that will allow you to get to like numerically approximate relative extrema. One quite common one is being gradient descent. And you may ask yourself, why go through a numerical method? This calculation seems fairly simple. Well, yes, I agree with you. In a case where we only have two variables that are changing, a system of two equations and two unknowns is fairly trivial. But what if you're dealing with an enormous data set that has 100 variables, and you have 100 variables and 100 unknowns? Good luck trying to solve that. Again, not that it's impossible, but it's a lot of work and it's computationally expensive, right? So by employing other techniques such as gradient descent, for example, you can make your life easier, and really I would argue make your life a little bit simpler. If you found this content informative, please support the channel. You can do that by liking this video, sharing this video with your friends and family, and subscribing to the channel. And if you're interested in one-on-one tutoring sessions, please follow the link in the description. Have a great day.